Have you ever tried using an old-fashioned map to navigate a modern city? That's how scientists began to feel about Bohr's atomic model. While Bohr's model did a great job explaining the hydrogen atom, it quickly lost its way when faced with multi-electron atoms like helium or lithium. The model couldn't explain the fine details in atomic spectra, especially when atoms were placed in magnetic or electric fields. These effects, known as the Seaman and Stark effects, showed us that something deeper was happening inside the atom. Bohr's idea of fixed circular orbits just couldn't capture that complexity. Another issue was the model's inability to predict the intensity of spectral lines, how bright or faint they appeared. Most importantly, Bohr's model ignored the wave-particle nature of electrons and the uncertainty in their position and momentum. These limitations forced scientists to look beyond, into the strange but beautiful world of quantum mechanics. Now imagine this, you're bouncing a tennis ball and suddenly someone tells you it's also behaving like a wave. That's the kind of revolutionary idea Louis de Broglie proposed in the early 20th century. He suggested that just like light behaves both as a wave and a particle, matter, including electrons, does the same. He introduced a simple yet powerful equation, wavelength equals Planck's constant divided by momentum, or in symbols, lambda equals h by p. This means the faster a particle moves, the shorter its wavelength. Though it sounded strange, this idea wasn't just theory. It was soon verified through the Davis-Germer experiment. In this experiment, a beam of electrons showed diffraction patterns when it struck a metal surface, just like X-rays do. This discovery laid the foundation for technologies like the electron microscope, which uses the wave nature of electrons to produce incredibly detailed images far beyond what light microscopes can achieve. Let's play a game. Try to tell me exactly where a buzzing bee is and how fast it's flying at the same time. Difficult, right? This is precisely what Werner Heisenberg formalized in his famous uncertainty principle. He said that it's impossible to simultaneously know both the exact position and exact momentum of an electron. Mathematically, this is expressed as delta x times delta p is greater than or equal to h divided by 4 pi. This wasn't just a measurement problem, it was a fundamental limit set by nature itself. It told us that electrons don't travel in neat little orbits like planets around the sun. Instead, their position is uncertain, and we can only talk about where they're likely to be. Max Born took this wave idea one step further. He argued that the wave function, represented by the Greek letter psi, doesn't describe where the electron is, but rather the probability of finding it there. So, psi squared gives us a probability density, a 3D map showing where we are most likely to find the electron. This gave rise to the concept of orbitals, regions in space with high probability of finding an electron. Unlike Bohr's fixed circular paths, orbitals come in various shapes, spherical for s orbitals, dumbbell-shaped for p orbitals, and more complex for d and f. These orbitals aren't just theoretical, they define the way atoms bond and form molecules. All of this was made possible through the Schrödinger wave equation, which combined both the wave and particle nature of electrons. The result? A model that works for all atoms, not just hydrogen, and finally explains the structure of the periodic table. Let's now get a little mathematical. Erwin Schrödinger crafted a beautiful wave equation to describe how electrons behave. Written in symbolic form, it is h hat psi equals E psi, where h hat is the Hamiltonian operator representing total energy, psi is the wave function, and E is the energy of the system. When Schrödinger's equation is solved for the hydrogen atom, it gives us quantized energy levels, just as Bohr observed, but with more accuracy and deeper insight. What makes this equation special is that it predicts not only energy but also shapes and orientations of orbitals. These solutions are governed by four quantum numbers: principal, azimuthal, magnetic, and spin, which tell us everything from the size and shape of an orbital to the direction and spin of an electron. Let's compare the old and the new. In classical models like Rutherford's or Bohr's, electrons were imagined as particles orbiting the nucleus in well-defined circular paths, much like planets around the Sun. But quantum mechanics transformed that view. Now, electrons are described as wave-like entities existing in orbitals, not orbits, with no fixed location, only a probability of where they might be. Classical models fail to explain why atoms behave differently under different conditions. But the quantum model explains it all, from electron configurations and periodic trends to the shapes of molecules and chemical bonding. Take, for example, the periodic table. Its entire structure is based on the arrangement of electrons in orbitals as predicted by quantum numbers. This shift from certainty to probability, from rigid orbits to fluid orbitals, is what truly revolutionized atomic science. Let's quickly revisit the journey that brought us here. We began with Bohr's model, a great start but not quite enough for complex atoms. Then came de Broglie, who told us that electrons also behave like waves. Heisenberg reminded us that we cannot know both where an electron is and how fast it's moving, leading us to embrace uncertainty as a fundamental principle. Max Born and Schrödinger helped us move from physical orbits to mathematical wave functions, giving rise to orbitals. These orbitals are now the heart of modern chemistry, guiding us in predicting chemical behavior, bonding, and periodic properties. As you see on screen, Bohr's model and Schrödinger's model differ in every essential way, from the nature of the electron path to the way energy levels are defined. I hope now you see why quantum mechanics was not just a tweak to existing models, it was a bold new framework that allowed us to understand the atom in all its complexity. Catch you in the next topic, where we'll continue exploring how chemistry builds everything, from the stars in the sky to the molecules in your body.